Hello, welcome back to the Dynamics video series. This video we're going to be talking about a continuation of what we did last video, which is time derivatives, including position, velocity, and acceleration. Last video we didn't include chain rule in any of the problems, so in this video we're going to include the chain rule to solve our problems. Um, I guess before we begin, it's kind of important to talk about how you should be using these videos. In my opinion, just watching these videos all the way through without actually attempting these problems yourself isn't a very adequate use of time. Um, if it suits you, and this is just personally how I studied as a student, what you can do is you can open these videos, check out the problem, maybe pause before I get started or before I start talking, and just attempt these problems on your own. If you get an answer, that's great. Play the video, see what I do, see if you get the same answer. I'll make sure that all my answers here in the video are correct. If at any point you're solving it on your own and you get stuck, you can unpause the video and then correct yourself there and pause it again and try and finish the problem on your own. That's just how I would do it, but with that out of the way, let's get into this problem. So this question is asking us that if a cart moves with a velocity of v equals x squared plus 1, it wants us to evaluate the acceleration when x is 2. Perfect. So like always, I'm just going to rewrite my given function. So I know that v, or velocity, equals my position cubed plus 1, right? And we want to find acceleration. So a little review. If you remember, to go to position, right, which is an x, that's the time derivative, right? So we're going to take a time derivative and we'll get to velocity, which is v. And then if we do another time derivative, or another TD, we can get to acceleration and a, right? So how can we do this? You would think, just based on the last video, that we could just take the first derivative of this function, and that would give us our acceleration function. But that's not how this is going to work, because in this case, our function is given in x, or in position, not in time like it was in the last video. So we can't take a time derivative of a position function. So we're going to have to use our chain rule. That's what this tells us. So let's see. We know acceleration, right, is the derivative of velocity with respect to time. Okay. We can't really get that yet. We have velocity in terms of position. But what else can we do? So we can also examine, right, that if we wanted to expand this a little more, we could say this as well, that the derivative, or acceleration, is the derivative of velocity with respect to position times the derivative of position with respect to time. The math works out in the way where these kind of cancel, and you end up with this function where you have dv over dt. So what can we do with this? All right, let's go back here. Can we do anything with these functions? So let's see. We know that we can find dv dx. We can get this term because that's just the first derivative of our term up here. All right, so that term's good. What about this next term? We don't really have a x function with respect to time, but we do have is we know that the time derivative of position, which is all this is just the time derivative of position, is just the same thing as the velocity. So how can we rewrite this? We can just say that this is dv dt, or dx, times the velocity. Yes. All right. So now we can plug stuff in. We know that this is our velocity. And if we want to get dv dx, we're just going to take the first time derivative of this function, right? Or not the time derivative, the first x derivative. So we can do that. When we refer back to our power rule, we're going to see that the first x derivative here is just going to be 3x squared. Okay, so now we can plug this value right here and our function that we started with into our v spot. So when we write it, we're going to get that the acceleration is equal to 3x squared times our velocity function of x cubed plus 1. Okay, so now we have our acceleration as a function of x, and we can actually plug in our given value. So we want to find out when x equals 2 what the acceleration is, and we can do that now. So I'm going to rewrite it really quick, where the acceleration is 3x squared times x cubed plus 1, right? And we're going to go ahead and evaluate that when x is equal to 2. So let's plug in our numbers. 3 times 2 squared times 2 cubed plus 1, right? I don't have my calculator on me, but I can just look to my answer key here. And this works out to being 108. So the acceleration value when time is 3 is 108. That's x equals 3, not time. All right. Okay, so this next problem is going to be a tad bit more tricky. So we're starting with acceleration in this case, and we're given some initial values. So let's read it. So a particle moves with the acceleration of a equals 4x squared, and then given that when x equals 1, v equals 2, we have to evaluate the velocity when x is 3. Sure. So how do we start this, right? So let's write our function just as a first thing. So we know that acceleration is equal to 4x squared. Now, this is similar to a problem we did in the last video. If we had acceleration as a function of time, we could just take an integral right away and solve for our velocity like that. But in this case, we can't. We're going to have to use our chain rule because we have acceleration as a function of x and not a function of time. So what can we do first? So we can analyze that acceleration, right? We remember it's just the time derivative of velocity. So let's write that down. So this is equal to the time derivative of velocity. And then we can expand this like we did before. This is the chain rule step. So we know that the dv dx is the same times the dx dt is the same as the dv dt. All right. And then we can take this one step further and realize that this term of dx dt is the same thing as velocity. So we can rewrite this again as dv dx times v. Okay, so let's bring this down. So we know 4x squared is equal to dv dx times v. All right, now I don't know if you guys can see this, but we only have really two variables now. We've kind of eliminated our acceleration. We have this term in x and this term in v, right? And we also have a dv term and a dx term. What we can do here is, as this is a separable, what's it called, derivative, we can actually move the terms that are like to the same side. So that's what I'm going to do here. So I'm going to rearrange this. I'm going to move this dx to this side. And now when I do that, we just multiply that to both sides. So times dx and times dx. We get what this is. So 4x squared dx equals v dv, right? So this looks very promising now. So we have a function in terms of x next to a dx and a function, well, not a function, a variable in terms of v and a dv. So at this point is the point at which we're going to start integrating, right? So let's do that over here. So I'll put this in blue. Let's say we're going to have the integral of 4x squared dx is equal to the integral of v dv, right? So we need to know our bounds here. So let's see what bounds we have. So our x to start and our x to finish. That's just I and f. And then our v to start and our v to finish. So initial and final velocity and position. So initially we're given our position is 1, And then we want to know the velocity when the position becomes 3. So we 1 and 3 respectively. And then our initial velocity was set at 2. And then we're actually looking for our final velocity. So this is just an unknown variable for now. So let's fill in with the bounds of our integral. So our x integral is going to go from 1 to 3. And then our v integral, velocity integral, is going to go from 2 to this unknown value, vf. All right, now we can start solving. So let's solve down here. So we know from our reverse power rule that if we do the left side first, the reverse power rule of this function is just going to be adding 1 to this exponent, so plus 1, and then dividing the coefficient by that number. So that's going to become x, and then the exponent is 2 plus 1, so 3. 4 divided by 3. Right? And then we're going to take this and evaluate it in our bounds from 1 to 3. And this is equivalent to, and we're going to take our v integral. This is going to follow the same step. So we just have a v there. So that's going to be pretty simply v squared over 2, evaluated from 2 to vf. Okay, we're almost done here. We're just going to expand this a little more. So on the left side, we have to evaluate this function of x from 1 to 3. You can do this the long way using the fundamental theorem of calculus. I'm going to simplify that and put it in a calculator for us. So when we put that in a calculator, we get that the left side value is just equal to 104 over 3. So that's the x side. And that's going to be the same as if that's going to be equal to the right side. So the right side, we do have a variable in there, so it's not going to be a whole number. We're just going to have, after you do the fundamental theorem of calculus, if you remember, it's the top minus the bottom. So vf squared over 2 minus 2 squared over 2. Perfect. So now we have one equation with one variable in it, so we can solve it here. If you put this in a calculator or an algebra solver, or you can just do it by hand, but for the sake of time, I'm going to use a solver. This becomes our VF is equal to 8.56. And that's going to be your answer for this question. Feel free to let me know if you guys have any questions here. Just you need to practice these a lot because these get kind of confusing, especially when you have to integrate. But that's going to be it. Bye.